All right, welcome back. So for lecture 16, inverse Laplace transformations. In this class, I'm just going to give you a method that the book outlines to do Laplace transforms. I'm actually going to deviate a little bit on the Laplace transform method um, because I find that the way they treat cosine and sine is more complicated than it needs to be. And so I used to teach it that way, but once I had to do like a substitute lecture for Professor Young, and I found that he taught it a different way, and I preferred his way, so then I started teaching it his way. And so I'm going to deviate a little bit from the book, but that already kind of tells you something that when you're doing inverse Laplace transforms, there's actually a lot of ways to do them. You've probably already been taught other ways to do it. Just use the way that's easiest for you. So basically, I'm going to give you a set of rules. It's up to you whether you follow them or not. As long as you can get the right answer, that's all that matters. There won't be any questions where you specifically have to use this method that I give you in this lecture in order to figure the inverse Laplace. I think Professor Macon also uses a different method than the one I use and the one that Professor Young uses. And so everything is fair game, everything works. You just want to use the method that you're most comfortable with. And I'm going to give you the one that I find the most straightforward way that I find that you can do inverse Laplace transforms. And when we say inverse Laplace transforms, we actually are talking about a very specific case, which I will describe in the next few slides. But before I do, just as a review of the previous lecture, we're going to do one more Laplace transform property, and it's actually a very important property that we will use to solve circuits. And we're going to actually go look at this property again in our lecture on what we call the transfer function. Okay, so let's say we want to do the Laplace transform of a convolution operation. So in particular, if we're given an f of t, and we know its Laplace transform, if we have a g of t and we know its Laplace transform, the question is, what is the Laplace transform of f convolved with g? So to do this Laplace transform, what you have to actually do is take the definition of the convolution and then apply the Laplace transform to it. But in particular, we can actually rearrange the variables like we have in the past by letting uh, lambda be equal to t minus tau, so that then t is equal to lambda plus tau, and d lambda equals t. And so if we do that, then this will become lambda. This would become uh, lambda plus t. Tau is lambda plus t, yeah. And, oh, 1 second, my cat is being annoying. Okay. And yeah, so, or actually we can just leave this one alone, the tau alone. And so now what we're gonna have here is f of tau, g's of lambda, and then this t we can replace with lambda plus tau. And so what we're gonna have here is actually we can replace this with e to the negative s lambda times e to the negative s tau. And so then what we're going to do is take all the tau integrations and put them together, and then take all the lambda integrations and put them together. And what we end up with is actually that the Laplace transform of the convolution is actually the Laplace transform of the product. And we're going to be using this extensively in the future. I will go over this proof again, actually, in one of the later lectures when we introduce what we call the transfer function. But one thing to kind of keep in mind now is that Laplace transforms map convolution to multiplication, and multiplying is a lot easier. So Not only do they help us solve differential equations, they also make convolutions a lot easier. Okay, so let's get started with the inverse Laplace transform. So this is actually the inverse Laplace transform. You have to do this contour integral, and here's e to the f s and then e to the st. And this, so basically, if you take a complex analysis class, this will be what will be given to you. That being said, we're never going to use this formula. And the only rule, as I alluded into the inverse Laplace the beginning of this lecture, is that there are no rules for inverse Laplace transforms. So yeah, there are no rules. Okay, so let's get started. So we have, so let's say we have a differential equation. What's going to always happen when we're going to analyze our circuits is that after a lot of algebra, we're going to get an f of s of this form, where we basically have a polynomial in s in the numerator. So we're just going to assume for now that the Laplace transform we want to inverse transform is of this form, where we have a polynomial in the numerator in terms of s, and a polynomial in the denominator in terms of s. So in the previous lecture, we had one that looked like, what was it? 30 divided by s plus 10. Another way to write that would be 30 divided by s squared plus 10s plus 0. In this case, kind of p0 would be 30, p1, there is no p1, and this would be a 0th order polynomial in the numerator, and in the denominator we have a 2nd order polynomial. So the first step when we get something like this is to find the roots of the numerator and denominator, or get it into this form. So we get the roots of we find the roots of the polynomial in the denominator, we find the roots of the polynomial in the numerator, and then after we find those roots, we're always going to assume that we can factor this function into this form, where we have a constant term plus 1 with each monomial term. Now, there are a few caveats here. One, what if we have repeated roots? So let's say R1 equals R2. Then, if R1 equals R2, we would have R1 squared here. And if R1 equals R2, which equals R3, then we would have kind of a A3 S minus R1 cubed, and so on. And then once we find this expression, we can use our inverse Laplace transform table to look up the answer. So what we will spend most of this lecture is how to go from here to here. That's effectively what we're gonna spend. So just remember, at this point, we're gonna assume that after doing all of our algebra, what we wanna inverse Laplace is something that looks like this. And we're going to look at different cases of how we can inverse Laplace. But to first do that, we first have to take the denominator and find the roots. We also have to find the roots of the numerator. In the next slides, I'm actually going to introduce some terminology that defines what we call these roots. And yeah. Okay, so let's look at the first case for computing inverse Laplace transforms. So let's just say we first found our polynomial, and then we found the roots of that polynomial in the numerator. And now we need to find the value of each of these constants. Now, the first thing I'm going to tell you is that A0 will be equal to 0 if n is is less than m. So if the order of the polynomial in the numerator is less than the order of the polynomial of the denominator, a0 is 0 and you don't even need to include it. So that's kind of the first thing you already can look up. If n is less than m, you don't even have to worry about it. Okay, so let's just assume for now that n equals m so that we have to keep it. So in order to find the a's for this expression, what we can do is a very simple heuristic, where what we're going to do is we're going to multiply both sides of this equation by s minus ri. So what's going to happen is that this sum that goes from k equals 1 to m now will only include, we'll have that a0, and then we're going to have all terms except for the one where ri is present multiplied by s minus ri. And then for the ai term, well, we're going to have kind of s minus ri divided by s minus ri. So that factor will actually cancel. And then here we have the product of all of the roots. So r1, r2, r to the m. So remember, this means the product of all of the roots. Well, now it becomes the product of all of the roots except the one with ri. And so what we can do now, since we have distinct roots, we can just plug in ri for s. And this expression has to be valid for all values of s. So on the left-hand side, we're going to get a number. So this will become a number. And then on the right-hand side, well, ri minus ri is 0. So this is 0 times whatever this is, which we don't know. So we're just going to be left with ai. And so that's going to give us that ai is whatever that number we got is on the left-hand side. And so we can apply this for each individual root until we get all the coefficients. And in the next slide, I'm going to go over an example, which will kind of give you a better understanding of the general idea. I think this kind of notationally looks very complicated, but the idea is actually very simple, as you will see in the next slide. Okay, so here's kind of the summary. Oh yeah, so sorry, I apologize. So before I get ahead of myself, once you find all the AIs, what you can do to find a0 is plug in any value for s, figure out what that sum is, figure out what the thing on the left-hand side is, and then just subtract the two to get a0, basically. Well, we're going to go over an example in the next slide, which I think explains it a little bit better if this pen allows me to work. So let's say I want to compute the inverse Laplace transform of this. So as you already noticed, the order of the polynomials are the same, which means that a0 will not be 0. Okay, so first we need to find the roots. So in this case, we have s squared minus 1, which gives us kind of s plus 1, s minus 1. That gives us s squared minus 1. And so that means that we want f of s of the form equal to a0 plus a1 s plus 1 plus a2 s plus minus 1, sorry. Okay, so let's find a1. So what we're going to do to find a1 is we're going to multiply both sides by s plus 1 as our heuristic set. So what we're going to have here is s plus 1 divided by s plus 1, s minus 1. So find a1. Okay, 1 plus 2s plus 4s squared. That has to be equal to s plus 1, a1 over s plus 1 plus a0 plus a2 over s minus 1 times s plus 1. Okay, now this cancels this out. This cancels this out. And now we're going to plug in kind of -1 or the value of the root into this expression. So we're going to have basically 1 plus 2 minus s plus, or sorry, minus 1 for -1 squared over -1 minus 1. So that's going to give us 1 minus 2 is -1, and then plus 4 gives us 3 divided by 2, and then -2 divided by -2, sorry. On the left-hand side, we're going to have here a1 times plus a0 plus a1 divided by -1 minus 1, and then all of that times 1 plus 1, which is equal to 0. So we're just going to be left with a1. So okay, so now we found a1. a1 is just -3/2. So we know that this is going to be equal to -3/2. Okay, so now we need to find a2. So how do we find a2? Well, we're going to apply the same trick, but instead now we will multiply by s minus 1. So we have here a1, and then this is a2, s minus 1, s minus 1, s minus 1. And then now we're going to evaluate at s plus 1. And so now, so we got that was 3/2. So now let's just do the math. Okay, so we're going to plug in, what is it? 1 to our equation. So remember, these cancel. So we're going to have 1 plus 2 plus 4 divided by 2, which is going to give us 6, 7, 7 over 2. And that has to be equal to a2. And remember, when we plug in 1 here, that's going to be 0. So now we have a2 is 7 over 4. Okay, now we need to find a0. But at this point, it's very easy because remember that this expression has to be valid for all values of s. So we've already used 1 and -1, so we cannot use that. But let's say we plug in 0. So we're going to have that 1 plus 2 times 0 plus 4 times 0 squared divided by -1 plus 0 squared is equal to a0 plus -3 over 2 over 0 plus 1 plus 7 over 2. This shouldn't be 4. I don't know why I got it 4. Divided by 0 minus 1. So on the left-hand side, we just have 1 minus, so we have -1 is equal to a0 minus 3 over 2 plus 7 over 2, which is going to give us that a0 equals 3, so that gives us 4/2, so a0 equals -2. Oh wait, sorry, not -2, -1. Yeah, so that we get 5/2. Wait, no, -3. I can't do math apparently. Yeah, so that we have basically -6/2 minus 3/2, that gives you 9/2. Add to that 7/2, you get -2/2, which is just -1. Okay, so that's basically it. Now, you might be asking, why did he plug 0 for s? Why not 3? I could have plugged in 3. I'm going to plug in 3 for s just to show you that I could have plugged in 3. I could have plugged in 4. I could have plugged in 2. I can plug in whatever I want. It's just that, as you may know, 0 is kind of a convenient quantity because it's very easy to do the math. But the math will still work out if I plug in 3 for f of s. So I'm going to show you that it does. If I can erase, maybe I'm not going to show you that it does. Oh no. This is just bringing back nightmares from the classroom where then the pen decides to stop working and then you're just like, no, what am I going to do? What am I going to do? But then it starts working again and then you're okay. And then the students just get a good laugh out of it. So I'm just plugging in 2. I'm not going to plug in 3. Too much math. But you could plug in 3 if you want to. So 1 plus 4, that's 5, plus 16, that's 21. So 21 divided by 5, or wait, sorry, 4 minus 1, that's 3. 21 divided by 3 should be equal to A0. And then you have 3 here, and then the 3's will cancel, so you have minus 1/2. And then you have 1 here, plus 7 over 2. And then, am I correct? 4, 3, yeah. So here, minus 1/2 plus 7, that's just equal to 3. Right? 6, 3. And then 21/2 is just equal to, well, 7. And that gives you 4. Did I do something wrong here? Okay, 1 plus 4, that's 5, plus 16, that's 21. 21, yes. Then 3, and then you get negative 3/2, and then you have s plus 1, which is 2. So that becomes a 3, and so that becomes negative 1/2, yes. And then here you get 2 minus 1, which is equal to 1, and then 7/2. And then you have 21, and then you have to subtract from that 3. And then, so 7, that becomes 4. Yeah, so here we're going to get that A0 equals 4. And let me see if I did the math on the previous one correctly, because maybe I didn't do that right. So we have kind of, if I had plugged in 0, 0, 0, and then I plug in 0, 0. Oh, I apologize. So because this is negative 1, this should have been minus. So this is 4. And then now, so this becomes 10 over 2 negative, which means that A0 has to be 4. So you see that we actually had the wrong answer previously, but now we got the right answer because I can't do arithmetic. But in both cases, the answer should have been 4. Cool. So that's how we do it. In the next slide, things are much more clean. So to find A1, so the first thing I did here was I found what the roots were for the denominator. Then based on the roots, I got that this should be the form that my answer should be in. And then what I did is I took this equation here and I multiplied by s plus 1. And so when I multiply both sides by s plus 1 on the left, these two cancel. On the right, well, these two will cancel, but then this one will stay and this one will stay. And then when I evaluate at s equals negative 1, on this side, when I plug in negative 1 here, I'm going to get 0. When I plug in negative 1, I'm going to get 0. So I'm just going to be left with the A1. And then on the other side, I'm left with this term, which I just need to evaluate at negative 1. And then I get the negative 3/2. I do the exact same thing for A2, except now I multiply by s minus 1. So I multiply my left side by s minus 1. That cancels out this one. and then I multiply my right side by s minus 1, s minus 1, s minus 1. These two cancel. Now when I evaluate at 1, this one becomes 0, this one becomes 0, so the only one that's left is a2. And then on this side, I just have to evaluate this at 1, and then I get my 7/2. And then finally, now that I know what A1 and A2 is, I can plug in whatever I want to F. In the last slide, we plugged in 0, and then at first we got the wrong answer, but then we got the right answer. And then we plugged in 3, and in both cases we got 4. So once we have this, to do the inverse Laplace, we can just go to the table. So this 4 is actually 4 delta. This 3/2 s plus 1, that's just e to the negative t u of t times negative 3/2. And then s minus 1 is just e to the t u of t times 7/2. Now, in general, for circuits, you're never going to have a positive exponential. This is just a math example. But the method still works when you have different roots. Okay, so let's look at a different kind of example. Let's say you have repeated roots. So if you have repeated roots, you're going to have to solve simultaneous equations. In particular, what you will have to do is you can use our trick, except now multiplying by the largest of the roots. And then you can find all the other simple roots. And then for the very last one, you just plug in different values of f of s and solve the simultaneous system of equations. As you will see in most cases, a0 will be 0, so this will actually end up being very simple, just as complicated as finding the initial, the a0 like we did in the previous slide. So now I'm going to go over an example just to show you better what I mean by it. Okay, so to do repeated roots, we're going to first deal with the easy ones, which in this case are going to be the highest order term of the roots and any simple roots we have. Okay, so basically here we have our f of s we want to factor, and we've already written it in a nice form where we know the roots. So we have this repeated root, so it appears as s plus 1 and s plus 1 squared. And then we have our a0. In this case, because this is a third order and this is second order, we already know a0 is 0, but we're not going to use that, just to drive the point home of how you would deal with this. Okay, additionally, we know that a1, a2, and a3, we can apply our trick to the highest order term by multiplying by s plus 1 term, s plus 1 squared both sides. So we multiply both sides by s plus 1 squared. We're left with something that looks like this, where this one will cancel, and then this one will only cancel one of the powers. And then when we evaluate at negative 1, this will become 0, this will become 0, and this will become 0. So we're only left with a2. And on the left-hand side, we just need to plug in negative 1. So we're going to have negative 1, negative 1, negative 1, negative 1. Oh, sorry, these cancel too. And then when we do that, we're going to get negative 3/2. Now, so now we found a2, which is negative 3 over 2. And now we need to find a3. So to find a3, we basically do the same trick, multiply by s minus 1. And then it will cancel out the a3 terms and won't cancel out any of the others. And when we evaluate at 1, this will become 0, this will become 0, and this will become 0. So all that's left is a3. And then we just need to evaluate this thing at 1. So we're going to have 2, 1 plus 2 plus 4, which is 7/4. Okay, so now we have a3, 7 over 4. So now, in order to get a1 and a2, we need two equations. Well, we're going to evaluate f of s at 0. So that's going to be 1 plus 2 times 0 plus 4 times 0 squared divided by 0 plus 1 squared 0 minus 1, which will give me negative 1. And that's going to be equal to a0 plus a1. So remember, we're going to plug in 0 here, and 0 here. So we have a1 minus 3 over 2 minus 7 over 4. And that's going to give us basically that, well, so this becomes negative 6 over 4, 13 over 4. So we have 13 over 4 minus 4 is 9/4. 9 over 4 equals a0 plus a1. So that's just after a little bit of algebra. Now we need a second equation, and to make our life simple, we've already used 1 and negative 1, so we have to use 2. We could use 3, but 3 is going to make the math more complicated, so it's not ideal. So let's just use 2, because multiplying by 2 is easy. So now we say that f of 2 is actually equal to 1 plus 2 times 2 plus 4 times 2 squared divided by 2 plus 1, 2 minus 1, and there should be a squared here. So we're going to get, on the top, we're going to get 21 over 9. So this is 3. 3 squared is 9. 1 plus 4 is 5, plus 16, that's 21. Okay, now in these, we're going to plug in 2, and we're going to plug in 2, and we're going to plug in 2. That's going to be a little more interesting because we're going to get a0 plus a1 over 3 plus, okay, or minus 3 over 2 divided by 9. And then 2 minus 1 is just 1, so plus 7 over 4. And so that's going to give us that this 3 becomes a 6. So we're going to have basically 21 over 9 is just really 7 over 3. And then we have plus 1 over 6. And then we have plus, or minus, sorry, 7 over 4, which is equal to a0 plus a1 over 3. And so that's going to give us, let's see, so minus 7 over 4. So if we multiply this by 2, we get 14, so we have 15 over 6 minus 7 over 4. And then we're going to multiply this by 2. We're going to get 30, and multiply this by 3, and we're going to get 21. So 30 minus 21 over 12. 30 minus 21 over 12, which is 9 over 12. Cool. So we have that 9 over 12 equals a0 plus a1 over 3. So we have these two equations here. We can subtract the two equations from each other. So at this point, it's just algebra. And that's going to give us that basically 9 times 3 over plus 9 over 12 equals minus a0 minus a0 plus a1 minus 1/3 a1. And then anyways, I'm just doing the arithmetic here. It's not really like, and then we have 2 over 3. And that's going to give us that a1 equals 9 over 4. Of course, we already knew that it would be 9 over 4 because we already know that a0 is 0. But anyway, yeah. So you can go through the arithmetic, and now you can find a0. So I'm going to do that cleanly in the next slide. Okay, so we had in the previous slide that we already knew these two coefficients using our old method, and what we needed to do is find these two coefficients. We plugged in 0 and got one equation. We plugged in 2 and got another equation. And then what we have to do is just basically solve these two equations to get our coefficients. Now remember, if the order of the polynomial on the denominator is bigger than the one in the numerator, so basically here we have 2, here we have 3, because these two are not equal, a0 is equal to 0. So we could have actually stopped here and said a0 is 0 and just said a1 is this. And that's actually what we ended up finding at the end. So here I went the extra step, but so that you know how to deal with multiple coefficients, you just do multiple evaluations of f, but you don't really have to do it for this particular case. Once you have it in this form, it's pretty easy. You use your lookup table and you can get your inverse Laplace. All right, so we have just one more case, which is when we have imaginary numbers. And for that one, we're going to use Euler's identity. So when you have complex roots. So in particular, when we have complex roots, we're going to basically deal with them in the same way we dealt with when we had real roots, except now our roots will be complex. So as you can see here, they are complex. I need to change my battery on this thing because it's getting kind of, yeah. Okay, when they are complex, and in general, these roots will come in pairs. So if we have negative sigma plus, and actually this should be plus sigma and plus sigma. So in our circuit, we're always going to have decaying exponentials. So our roots will always be negative some value. And I guess sigma in this case is a negative number, so we can leave it like this. But in general, you know, just remember that it's always a decaying exponential. And then we have kind of some j omega terms here. Okay. Now we can use the same method we applied in our for the real case, except now we're going to have to use Euler's identity in order to convert this into a sine and cosine form, which is what the book is typically looking for and what we're going to be looking for in this class. So I'm just going to go over an example of this. So let's say we had to solve this particular equation. As you know, this polynomial here, if you were to use the quadratic formula, you would get that it's got a complex roots. And so to compute the inverse Laplace of this, what we're going to do is we're going to assume that f of s is of the form a0 plus a1 divided by s plus 1 minus j plus a2 s plus 1 plus j, and then plus a3 s plus 1. Now, at this point, you should know that the order of this polynomial is 1, the order of this polynomial is 3, so a0 equals 0. I'm not going to deal with it. At this point, you should just know that when the order is lower, this is already 0, so we can already say that that's 0. So we already got one of the coefficients. Now, let's first get this a3 coefficient. So that one's pretty straightforward. We multiply both sides by s plus 1 and evaluate at negative 1. So we have s plus 1 divided by s squared plus 2s plus 2, and then s plus 1, done, done. And we're going to evaluate it at s equals negative 1. That should be equal to a1 evaluated at s plus 1 minus j times s plus 1 plus a2 s plus 1 plus j s plus 1 plus a3. And then we have the s plus 1, which cancels. And this also has to be evaluated at s equals negative 1. And so in this case, when we plug in negative 1 here, we get 0. Same thing here, we get 0. So we're left with a3 equals 1 over negative 1 squared plus 2 times negative 1 plus 2. So 2 minus 2 is 0, so this is just equal to 1. Okay, so a3 is equal to 1. And now we have to get a1. Well, to get a1, we're going to use the same trick. So to get a1, we use the same trick. So here we're going to have s plus 1 minus j, s plus 1 plus j, and then, yeah, so we're going to multiply by s plus 1 minus j, s plus 1 minus j, s plus 1 minus j, and then evaluate at s equals negative 1 plus j, negative 1 plus j. So s plus 1 minus j cancels out this one, and so we're going to have 1 over negative 1 plus j plus 1 plus j, negative 1 plus j plus 1, and then that's going to be equal to, well, here this will be 0, and then this will be 0. Wait, no, this one will cancel, and then this one will be, these two will be 0, so we're going to be left with a1. And then when we evaluate this here, we get 1 over 2j times j, which is equal to negative 1 over 2. So we're going to have that a1 equals negative 1 over 2. Now, this is kind of like a more of a professional trick. a1 and a2 will always be conjugates of each other, so you already know that a2 will be negative 1/2 because it's a real number. So at this point, you don't really have to go through with it, but you can go through with it and see and confirm that indeed it is 1/2. So I'm going to plug in plus 1, and then this becomes minus, so that then the pluses cancel. Yeah, plus 1. And then this one no longer cancels. This becomes a plus, this becomes a plus, this becomes a plus, and then this becomes a minus. And now this one's still 0. This one cancels, and then this one becomes 0. So this becomes a2, and now we need to plug in negative 1 minus j plus 1 minus j, right? Wait, hold on. So we're doing a2, so plus j, and then so there should be a plus 1, plus j here. Yes. Okay, negative 1 plus j, and then this should be minus j, sorry. Okay. So there should be a minus j here, and then this we're plugging minus j, so here minus j. Okay, now let's see what the math works out to. So this becomes negative 2j. Okay, sorry, I just skipped the slide, so we're gonna go ahead and look at it here. Yeah, so now we have, when we plug in here, when we multiply by this, these two cancel. So now we're gonna plug in negative 1 minus j, so the negative 1 cancels this, and this becomes negative 2j. And then this becomes negative j, and so then we get negative 1/2. And then for the previous one, we had this one cancels out this one, and then we plug in negative 1 plus j, so negative 1 cancels the 1, and then plus j becomes 2j, and then this becomes just j, negative 1 plus j becomes j, so you get negative 1/2. So at this point, now you have the three coefficients, which are negative 1/2, negative 1/2, and for the third one, what we got in the previous slide. So we have the three coefficients. And now what you can actually do is just use Euler's identity. So this is just this and this, which gives you e to the negative t, u of t for this one. And then you have cosine minus cosine t, which would be the combination of t's times e to the negative t. And that's it. That's how you do the inverse. Okay, so let's look at one more example. At this point, we know that this is a lower order polynomial than this one. So this is a third order. This is second order, so we already know a0 is 0. And now we just kind of multiply both sides by s plus j and evaluate at negative j. So that's just going to give us, remember that this one will be 0, this one will be 0, and then these two will cancel. And so that's just going to give us that a1 equals, so we're multiplying by s plus j and evaluating at negative j, so we have to remove this one. So we're going to have 1 plus 2 negative j plus 4 negative j divided by negative j minus j, j plus 1. And so that's going to give us that this is equal to, well, this negative 3, because this is negative 4, so it's a squared, sorry. Negative 4 plus 1, that's negative 3, plus 2 minus 2j, divided by negative 2j, and then j plus 1. So we need to multiply this by the complex conjugate to get rid of this term on the numerator. So we have 1 minus j, 1 minus j. So that's going to give us, so this becomes j minus 1 plus 1 plus 1 minus j, so that becomes 2. So we have negative 4j in the denominator, sorry. And then we have minus 3 minus 2j plus 3j, and then plus 2. Is that correct? Minus minus becomes plus, yes. Minus minus become plus. Oh, I apologize. This should be minus j here, and this should be plus j, and so this should be plus j. And so then now we're good. Okay, because remember we plugged in negative j. So there should be a negative j here. And so that means that this should be actually minus 3j and minus 2. So, wait, sorry. 3 minus 3 minus 3j minus 2j minus 2. Yes, okay, good. So now we have minus 5, and hold on, so 3, negative 3, good. And then we have minus 2j, okay. Then j times that is negative 3j. J times this becomes positive 2. Yeah, okay. And so, wait, j times that, j times negative becomes positive 2, yes. So negative 5j plus 1 over 4j. so we have 1. So now we know that this is going to be actually equal to, we can multiply both top and bottom by j, so that we have basically that a1 will be equal to 5 over 4 plus 1 over 4j. And we already know that these two are complex conjugates, so we can already guess that this is going to be 1 over 4 minus 1 over 4j. So you don't even have to do it, but we're just going to do it for sanity check. Okay, so to do a2, we multiply both everything by j minus 1, which gets rid of this, and then we evaluate at j. So a2 will be equal to 1 plus 2j plus 4j squared divided by j plus j plus 1. And I remember that we're going to have to multiply this by a conjugate. So j, to get rid of the complex in the denominator, so 1 minus j, and then 1 minus j. This again gives us the negative 3 that we had before. And then, so this becomes 4j in the numerator. So remember that this is just 1 plus 1. And then this is just 2j. So it's already 4j. And then here we have negative 3 plus 2j times j 1 minus j. So that's just going to give us, well, negative 3 plus 2j plus 3j, right? And then the 2j's, j times minus j becomes plus 2. And so we're going to have negative 1 plus 5j divided by 4j. And indeed, that's just going to be, we multiply top and bottom by j so that we get, what is it? Negative j over 4 plus, or sorry, top and bottom by j. Oh my God, what did I do here? There should be a minus here. There should be a minus here, and there should be a minus here, and then this becomes a minus, and then this becomes a plus. Okay, negative 4j, so we multiply top and bottom by j. So, oh, wait a second. When we multiply by j, this becomes a positive 5. And this stays positive. So actually these signs were correct. Yeah, and then this becomes negative. Okay. So we multiply the top and bottom by j, so this becomes a, or by negative j, let's just say, so that this becomes 1/4 j, then negative j, so that becomes plus top and bottom by negative j, so this becomes 1/4. 5 over 4. I might just, what did I do here? 5j. Yeah, so that's correct up to now. Okay, now if we multiply this by j, I'm going to go back here and just do this math here. If I multiply this by j, I'm going to get 4 in the numerator, and then I'm going to have here, I have negative 5j, which if I multiply by j becomes positive 5. And then I have negative 1, which if I multiply by j just becomes j1. Okay, so this is positive, this is negative, and then this is positive. So indeed, they are complex conjugates of one another. So we get j over 4, negative j over 4. 5/4, 5/4. Okay, so that's basically how you do these. As you can tell, there's a lot of arithmetic, but it's not really that complicated as long as you follow the heuristic. So here I show kind of the derivations on the previous slide much more cleanly, but the same idea applies. Multiply by j plus 1, evaluate at negative j. Multiply by j minus 1, evaluate at j. Multiply by s plus 1, evaluate at negative 1. And then that's going to give you the three coefficients. Once you have the coefficients, you get the inverse Laplace, and then you're done. So here's kind of the inverse Laplace of this. So here's the coefficients plugged in. Now, we have to write this in terms of Euler's identity. So we have to kind of write the two parts in terms of the real part and the imaginary part. The imaginary part will correspond to the sine part, and the real part will correspond to a cosine part. Now, one thing to note here is that if you look at the s plus j coefficient, half the real part is the value of the cosine part, and half the imaginary part is the value of the, the 5/4. This is 5/4, 5/4, and this is equal to 1/4. So if you look at this closely, the value of the coefficients is actually twice this, and this should actually be over 2, not over 5. I apologize. Because over 4, 8. Sorry, I apologize. Actually, this is correct. It's just that there should be a half. So if you put, because this should be 2 times 4. And so then you end up with, this is actually the sine. And so, yeah, so this should actually be 5/4. Twice the coefficient, so this should actually be 5/2, and this should be 1/2. So I apologize, this is a typo, it should be 5/2. So if you look, half of this value is the coefficient in front of the cosine. So this is just 10/8, sorry, twice, not half, sorry, twice. And then twice of this value is the sine coefficient, or negative 2/8 times 2, which is just 1/2, and this is just equal to 5/2, or negative. So if you always look at the s plus j coefficient, or the one with the positive root, the real part is the one that gets the cosine factor. The imaginary part is the one that gets the sine factor. And you can avoid doing all this extra math. So that's just something that after you do a bunch of problems, you're going to notice that, and then you don't have to even worry about finding this coefficient. Okay, so that's basically it. That concludes our Laplace transform. Just as a reminder, we went over all of these. We also went over how to find the inverse Laplace. And then we have this duality concept, which is basically kind of marked by this table here, where you have that if you do something in the time domain or in the S domain, if you do that same thing, you get the same effect on the S and the T domain. So that concludes all of our lectures for Laplace. The next few lectures, we're going to actually start using this math to solve circuits.